Hello, today we are covering 8.4 trigonometry. You guys will be able to find trigonometric ratios using right triangles, and we'll use trigonometric ratios to find angle measures of right triangles. Now, trigonometry is a whole semester class that you take with pre-cal in high school. So this is just an intro to that. I do want to say though, out of everything in geometry, it is most important that you are able to recall this trigonometry section as well as the previous special right triangle section, because those will continue to show up in future math classes. So we have new vocab: trigonometry, trigonometric ratio, sine, cosine, tangent, inverse sine, inverse cosine, and inverse tangent. So trigonometric ratios, the word trigonometry comes from two Greek terms, trigon, meaning triangle, and metron, meaning measure. The study of trigonometry involves triangle measurements. A trigonometric ratio is a ratio of the lengths of two sides of a triangle, of a right triangle specifically. One trigonometric ratio of this triangle ABC is AC over AB, okay? Now we'll do more with that in just a minute. So by angle similarity, a right triangle with a given acute angle measure is similar to every other right triangle with the same acute angle measure. So trigonometric ratios are consistent for a given angle measurement. So before we had the special right triangles, 45, 45, 90 and 30, 60, 90, those are pretty simple proportions that we can set up and solve, but anything that is not those special rights, we need to use trigonometry to find. So notice they marked out similar sides, similar triangles here. And the names of the three most common trigonometric ratios are given below. So we have sine, cosine, and tangent. There are a few others, but we're going to cover those. So in triangle ABC, or that is a right triangle with acute angle A, then the sine of A, written as sine A, is the ratio of the length of the leg opposite A to the length of the hypotenuse. So if you are standing at angle A, you are going to have the opposite over the hypotenuse. As you'll see right here, if you were standing at angle B, you have something else. Notice you don't stand at the 90 degree. You only stand at the other two angles. Same thing with cosine, except this time it's the ratio of the adjacent to the hypotenuse, and the tangent is the ratio of the opposite to adjacent. Now, you might be asking, how am I supposed to remember these? Well, we have a nifty little saying, so ka toa. Okay, this stands for sine. Oops. Opposite over hypotenuse cosine, which is shortened COS, is adjacent over hypotenuse, and then we have tangent, which is shortened TAN, which is opposite over adjacent. So if you can remember SOHCAHTOA, then you know how to set up your ratios, okay? So we are going to express each fraction, or each as a fraction and decimal rounded to the nearest hundredth. So we are going to be standing at angle L. I'm going to rewrite my SOHCAHTOA up here. Notice I have sine of this, so sine from angle L is going to equal opposite. Opposite's the one across the way, over hypotenuse, which is 37. Now we need to write that as a decimal, so we take 12 divided by 37, and we get, okay, nearest hundredth, that is 2 decimal places, 0.32. Okay? Now if we want to go cosine of L, notice we're standing at the same angle still, but we go adjacent. So adjacent is the non-hypotenuse side that is right beside that angle, or helps form the angle, and then the hypotenuse. So we have 35 over 37. We want to write that as a decimal. We end up getting to the 100th, 0.95. And then if we want to take the tangent of L, notice we're still standing at angle L. We want to do opposite over adjacent. So we have 12 over 35 equals, I don't know, let's figure it out. That equals 0.34. All right, so notice, from that angle L, we had our opposite, we had our adjacent, we had our hypotenuse. If we then go stand at angle N, our perspective changes. We now have the opposite over here, we have the adjacent here, and we have the hypotenuse. The hypotenuse doesn't change, it's always across from the 90. But the opposite and adjacent are switched. So the sine of N is equal to opposite over hypotenuse, which is actually going to be the same decimal as cosine of L, 0.95. The cosine of N is adjacent over hypotenuse, which is the same as sine of L in decimal form. And the tangent of N, opposite over adjacent, is the reciprocal of the tangent of L. Which we end up getting 2.92 as our solution there. Okay, so that is how you figure out what ratio you set up. It's just from where you are standing, if you have that perspective. We're going to do 3 more like this. So we have find sine of A. We're standing perspective A. We still have SOHCAHTOA. So from A, opposite is 12. Adjacent helps form the angle but is not the hypotenuse. And 20 is the hypotenuse. So SOHCAHTOA tells us we need opposite over hypotenuse, so 12 over 25. We'll find them all as decimals in just a minute. Cosine is adjacent over hypotenuse, which would be 16 over 20, and if we reduce this, we get 4 over 5. And then tangent is opposite over adjacent, so 12 over 16, and when we reduce, we get 3 over 4. So I know that this one is actually 0.8, this is 0.75. The last one I don't actually know, so we need to try that out. It's just under 0.5, I believe. Yep. And you're probably thinking, what is the point of writing these fractions out? Well, we can use it. So that was just getting us to remember SOHCAHTOA, figure out the ratios and things. Now we can solve using our sine, cosine, and tangent. A fitness trainer sets the incline on a treadmill to 7 degrees. The walking surface is 5 feet long. Approximately how many inches did the trainer raise the end of the treadmill from the floor? Now I want to point out that we want our solution to be in inches. So probably before we even start, we should change this from feet to 60 inches just so we don't get ourselves confused. So now, we can use our idea of sine, cosine, and tangent. I'm going to write out my SOHCAHTOA again. All right, so that way I can pick what ratio I need to use. It's not telling me to use the specific one. So this is where I am looking from. I need to find the opposite side length, and I am given my hypotenuse. So if I have opposite and hypotenuse, I know I need to use my sine trigonometric function. So I have sine of my degrees. Now just follow along real quick. We haven't had a problem like this yet. Equals my ratio opposite over hypotenuse. Now I do just need to solve for y, so I multiply by 60 on both sides. And I can go ahead and use this to solve for the inches off the floor. So y is actually just going to equal 7.31 inches because we wanted it from hundredths. Okay, well, never mind. It doesn't say 1/100th of an inch, but I want it to the 100th of an inch. So 7.31 inches. Alrighty. So we're going to try another one just so you can see an idea. The bottom of a handicap ramp is 15 feet from the entrance of a building. If the angle of the ramp is about 4.8 degrees, how high does the ramp raise off the ground? So, once again, we are here. This is our perspective. We are trying to find how far it is off the ground. I'm going to call it x. I am trying to find then the opposite side, and I am given the adjacent side length. So, if I rewrite out SOHCAHTOA, this tells me I need to use tangent. Now, really quick, I do want to point out this also wants to the nearest inch, so I should take 15 times 12 to go ahead and switch it into inches. So this is 180 inches. And I can set up my trig, okay? So I need tangent of my degrees equals opposite over adjacent. And now I just solve for x by multiplying by 180 on both sides. So I now have 180 tangent of 4.8 equals 15.12 inches is how high it is off the ground. Okay? Now, find the value of x to the nearest hundredth. These aren't story problems anymore, but we are going to do the same thing. We have our perspective here at 25 degrees. I am trying to find my opposite. I am given my adjacent. So once again, if I rewrite SOHCAHTOA, I am going to use the tangent. So I have tangent of 25 is equal to opposite over adjacent. Go ahead and solve. So I end up getting 18 tangent of 25 degrees is equal to 8.39 for x. And then if you wanted to, you could find that other missing side length by just simply using Pythagorean theorem. Or you could use another trig function to find the hypotenuse. And then on this last one, we have a new perspective here, 70. I'm trying to find my hypotenuse given my adjacent side. So I'm going to use cosine. So I have cosine of 70 is equal to 15 over x. All right, now notice this problem, our ratio is set up differently than all the rest we've done. So we're gonna have a little bit different work. Follow along here. I go ahead and I multiply x up. So it's not in the denominator anymore. So I have x times cosine of 70 is equal to 15. Now I still do need to get x by itself, so then I divide cosine of 70 on both sides and get my solution. It's kind of like we were just cross multiplying. So if you had instead looked at it this way, cosine of 70 equals 15 over x, and you had said, okay, I'm going to cross multiply to solve, you would end up getting the same setup as we have here. So either way, totally valid. You end up then just plugging this into your calculator a little differently. So you end up taking 15 divided by cosine of 70, and you end up getting that missing side length is equal to 43.86. Okay? So then you could do Pythagorean theorem if you wanted to find that third side length, or use another trig function to really check. All right, now part 2, we are going to use inverse trigonometric ratios. So in example 2, we found that tan of 30 is equal, so tangent of 30 degrees is equal to 0.58. It follows that if the tangent of acute angle is 0.58, then the angle measures approximately 30 degrees. So if you know the sine, cosine, or tangent of an acute angle, then you can use a calculator to find the measure of the angle, which is the inverse of the trigonometric ratio. We are going to use a calculator to find the measure of angle P to the nearest tenth. So this is our perspective. We are given our adjacent and our hypotenuse. This means in our SOHCAHTOA, we are going to use our cosine trig function. So we are going to use the inverses. You use the inverses to find angle measure. The inverse of our trig function, adjacent over hypotenuse, will actually just figure us the measure of angle P. Okay? So if we pull this up, we can go inverse of cosine and then plug in that 13 divided by 19. And it gives us that the measure of angle P is equal to 46.8, we'll say 0.83 and round up. Oh, it says tenth. Never mind, we'll just say 0.8 degrees. If we were then to find Q using a different trig function, we know it would have to add to equal 90 with 46.8. All right, so we are going to use a calculator to find the measure of angle D to the nearest tenth. So this is our new perspective. We have opposite, we have hypotenuse. If we scroll up, we know we have to use our sine, inverse sine trig function, I should say. We take the opposite over the hypotenuse, grab our calculator, do the inverse sine, inverse sine of 16 divided by 23, and we end up getting that degree is 44.1. Now these are two different problems, that's why they do not add to equal 90, but this is actually the measure of angle D. Okay? Solve the right triangle, round side measures to the nearest hundredth, and angle measures to the nearest 10th degree. So we want to find angle A. Why don't we just start there? we have opposite and adjacent given to us, so with SOHCAHTOA, we know we need to use the tangent. So we have the inverse tangent of opposite over adjacent. We need to find this guy. Is equal to 29.7. Then you could actually just finish solving using other techniques. I'm going to keep using trig stuff just to show you everything out. We need to find the measure of angle B, and maybe I should mark this out. Measure of angle A. We need to find the measure of angle B. We still have opposite and adjacent, but this time they switch around from the perspective of angle B. So we have the inverse tangent of opposite over adjacent. Oops. We can figure out this. We end up getting 60.3. Notice these two answers add to equal 90. We know that has to happen because this still is a triangle. That still has to hold true, so we're good there. And then, because you do have two side measures given to you, you could just go ahead and use Pythagorean theorem to solve for this missing side length. And that's not a bad idea. I actually think I'm going to go ahead and do that as well, just because why not use something we know? So 4 squared plus 7 squared is equal to c squared. 16 plus 49 is equal to c squared. So what is that? 65 is equal to c squared. So c is equal to the square root of 65. Let's pull this up. And we get this, we need to round it to the nearest hundredth, so 8.06. Is what the length of AB is. So I'm actually going to mark this instead of C. I'm going to mark it AB for that segment. All right, and that is how you solve the triangle. We have one more like that. Solve the triangle. Round side measures to the nearest hundredth and angle measures to the nearest tenth. So we can once again just do Pythagorean theorem. I'm going to do that to start. Why not? So 8 squared plus 11 squared equals c squared. Go ahead and pull up our calculator. We get that c is equal to 13.60, which is actually just the length of AB. So I'm going to go ahead and rename this AB. And then once again, I have to find my angles, so I am standing with perspective to angle A. That means I have opposite, I have adjacent sides. I'm going to use my tangent function then. So I have tangent, inverse tangent, I should say, of opposite over adjacent will equal the measure of angle A. So the measure of angle A is equal to 54 when you round up. So 54 degrees. That means if we find the measure of angle B, new perspective, our opposite and our adjacent switch places, still using inverse tangent. this is equal to opposite, oops, sorry, not equals. Inverse tangent of 8/11 will equal the measure of angle B. There we go, that's more like it. Is equal to 36 degrees. Okay, notice these once again. Add and equal 90, we knew that must happen, and it does. So real quick, normal tan functions, or normal trig functions, I should say. We'll say sine, cosine, and tangent. These solve for side lengths. You can scroll up to the beginning of the notes and see that. Inverse trig functions. Inverse of sine, inverse of cosine, and inverse of tangent solve for angle measures. And that's how you can keep track of how and what you need to use where. Okay?